Hi everyone. In this video we discuss zero padding, which is basically a very simple yet very important mechanism used in convolutional neural networks. And the motivation is very simple. So basically, if you have a stack of convolutional layers, and where the convolutional kernel, let's say one dimension, the convolutional kernel has size k, right, or has width k, then if you don't do any modification, the size or the number of units in the layers has to reduce by k minus 1 between consecutive layers, right? So for example, in the example right here, we start out with 7 units in the input layer, right? In order to apply the kernel of size 3, I have to cut 1 unit from each side on the edges, right? So the next layer will be 5 units, and then the next layer would be 3 units, and then the next layer would be 1 unit, right? So in this case, you cannot have more than 4 layers, and the last layer will only have 1 unit, right? So so this becomes a problem, right? Because so remember when we discussed, for example, fitnets, right? In fitnets, you have the teacher network. It's a shallow and wide network, and then the student network is a thin and deep network, right? So whenever you have thin meaning the layers are small, and deep meaning many layers, right, stacked on top of each other. If you have a thin and deep convolutional neural network, then zero padding becomes a very serious issue, right? Because it limits the depth of the neural network, right? And as we discussed before, these thin and deep networks can actually play a great role in applications where generalization is very important, and we have a lot of prior belief about the final solution, how it looks like, right? So they can be very effective in these cases, where careful engineering is used to design the thin and deep network, and then it generalizes really very well. So there are multiple ways to handle this issue. And the idea of zero padding is very simple. Just add units on the edges. So add units right here on the edges with zeros, okay? And there are many. So if there is no zero padding, then in MATLAB terminology, which you might find it used a lot, this is called valid convolution. Now, the other 2 types of convolution depend on the type of zero padding that you introduce. So if you decide to make the consecutive layers have the same number of units, so you fill, in that example, you fill 1 unit on the edges, right? Then you have what's called same convolution, okay? Now, let's see the same convolution. What's the problem with it? The problem with same convolution is that basically the borderline pixels, right, will contribute to fewer output units than the input units near the center, right? Because the ones near the center, so here this one near the center contributes to 3 units, right? Whereas a unit near the border will contribute to only 2 units. So and then so that can become a problem, because as you go deeper, right, and let's say I go like to the 4th layer, to the top unit here, the receptive field of this unit in terms of the input units, right, will be mostly affected by the units at the center. So if you have an image, the pixels at the center will be more impactful than the pixels at the edges, because you do the zero padding at the edges to keep the same convolution. Now, in order to alleviate this, or one option to alleviate this, is what's called full convolution. And full convolution basically means that the output of the convolutional layer will have more units, so that you guarantee that the edges affect the same number of units. So I add 1 more unit here, right? So that this unit here will affect also 3 units, in the layer afterwards. And this unit here will affect also 3 units in the layer afterwards. What's the problem? The main challenge with full convolution is that if I look at these new units at the edges, right, this unit is affected only by 1 input unit. And this unit is affected by 2 input units, while each of the other units is affected by 3 input units, right? So it's hard to optimize. And remember, the weight of there is parameter sharing, right? So that edge right here is the same as that edge right here, right? So this edge, right, is the same as this edge. This edge is the same as this edge, right? So while learning, these units at the edges will affect the learning of the kernel, right? So it becomes difficult or challenging to learn the same kernel for both the units that have 3 weight parameters connected to them and the units that have only 1 weight parameter connected to them, right? So to recap, why is zero padding introduced? Because you want to maintain the size of the layers, or you want to maintain the ability to increase the depth as much as possible in thin that have lower number of units or small number of units per layer, and deep convolutional neural networks. You don't want the edge problem to limit the depth of the network. So there are 2 types of zero padding that are known. One is called same convolution. If there is no zero padding, the convolution is called valid convolution. Same convolution that basically maintains the size of the layer, right? And full convolution that basically maintains or guarantees that each input unit will affect the same number of output units in the output of the convolutional layer. The problem with same convolution is that the edges will not contribute as much as the center. The problem with full convolution is an optimization problem, because the kernel, it's hard to learn the same kernel for both the units at the center and the units at the edges. Thank you.